I think it's from how somebody.
So average rate of change, right? Go ahead and click everything all the way close. Everybody's undivided attention, please. So average rate of change. Average rate of change is just change in output over change in input. We've looked at some examples. We've had, even going back a little ways, we've had some examples with graphs where we're just going to find the slope of the line connecting 2 points. Or you can just think of it as the change in the y coordinates. How much did the y coordinate change over how much did the x coordinate change, right? So let's review one more example, and this is just one that we looked at the other day, but I want to make sure everybody gets this. Let's look at one where it's not graphed, where they're just giving us. We're gonna rely on Desmos to help us out here. So we're gonna use this last definition, which is change in output. So it's gonna be the value of the function at its final input minus the value of the function at the starting input divided by the change in the input values, the final value minus the starting value, okay? So that's what we want to, in fact, let me take a picture of that to put on the next page. All right, so there it is. Now let's look at this problem. There's our definition, right? We can do this one in Desmos. Now they're giving us, this is the one, I think we looked at this the other day, right? I think we did. So we've got this function here that's giving us yearly profit in millions of dollars, and that's the output is profit. The input is year, right? The year since 2010. And so let's identify, what would X1 be? What's our starting input value? 9. And X2, our second or our final input would be 13, okay? And so we want to know what's the average rate of change. Well, we're just going to use its definition, and we'll use Desmos. Instead of F, ours is going to be P of X, not that it makes any difference. So in Desmos, all we have to do, it's this simple, all we have to do is define the function, right, which it's already done, it's right up here, right, all this stuff right there. So P of X equals negative 0.11x squared plus 3.84x minus 1.03, okay? And then we're literally just going to do this, right? We just literally want to do that to it, okay? So we're going to make that expression. So we're going to say the quantity P of X2 you told me was 13. So P of 13 minus P of 9, that's my starting value, right? I'll divide the whole thing by final input minus starting input, so 13 minus 9. And it gives me the answer right there. You guys see that? So it's 1.42. It wants it rounded to the nearest tenth. And so what's that tell me that the answer is? 1.4. Right. You guys see that? We'll put that in the notes here. So if I take a picture. Okay, so that just tells me that my answer is right from there. What's that color? Right, but it's already in millions, and so it's 1.4 million. Yeah. Okay. All right, so end behavior. We could probably skip that one. Let's just do one example. So what about this one? Just tell me what's going on here. So as x approaches infinity. Now think about this in terms of the blue graph. And there's a red asymptote there that's helping us out with understanding the behavior of the graph, right? So, but the ant's walking along the blue graph. What does this mean? As x approaches infinity, what's that talking about? What's that asking the ant to do? As
Walk.
x approaches infinity, walk where?
To it.
But in what direction?
Right.
To the right. Okay, as x approaches infinity, that means we're going right forever. As he goes right forever, what is f of x doing? So this is the horizontal behavior, this is the vertical behavior. So his horizontal behavior is he's moving to the right forever. What's his vertical behavior when he gets way out there? What's f of x doing? As the ant trots along this thing forever to the right, what's his y value? Approaching, because that's what that means. As x approaches infinity, f of x approaches what? 4. Yeah, right? His y value is approaching 4. He's getting inching closer and closer and closer to y equals 4. Okay? So he's going vertically to there, right? Now what about this statement down here? Let's look at this one. So now it's asking, as x approaches negative infinity. So what's that asking us? As the ant goes where? To the left forever. What's y doing this time? Yeah, as he goes to the left, the function's taking him up forever, right? So what is f of x, or y, approaching? What's it doing? You told me it's doing that, right? Forever. Infinity. Okay, that's it. Okay, so that's end behavior. All right, for today. For today, oh, what about this end behavior here? What do we say about this? As x approaches infinity or negative infinity, does this even make sense? No, the graph doesn't extend out there, right? The graph stops at -7 and +8. So that would be NA, right? There is no end behavior. Okay, so today, really simple stuff, really simple stuff. If you just follow this very closely, you're going to get this right away. So all we're looking at here are characteristics of function graphs. And there's two kinds of things that we're going to address. So one of them is positive and negative valued functions. So this question is asking, use one or more inequalities to write the intervals on which the function is negative valued. So what in the world does that mean? First of all, we have to decode that, that sentence. What does that mean in terms of math? When is a function negative valued? I'll ask you two questions. When is x negative value? X is the horizontal variable. So where on the xy plane is x negative value? To the left of what? 0. Okay, to the left of 0, right? You might even say to the left of the y-axis. Everything over here, any point in quadrant 2 or quadrant 3 over here is going to have a negative x coordinate, right? Okay, but that's not what this is asking. This is asking where the function, and f of x equals y, right? So the output of the function is going to be the y component. Where would y components be negative? X is negative to the left of the y-axis. Where is y negative? Below the x-axis. So down here in quadrants 3 and 4, that's where y is negative. So any place where the function is below the x-axis, that's where it's going to be negative value. So all we have to do is just identify the places on the graph where the ant would be sort of below sea level, right? Below the x-axis. Okay? So where's that going to be? And we don't have to be real fancy with the math. Just describe it right now using words. It doesn't have to be too. We'll make it mathematical in a second. But tell me a region of the graph where the ant would be walking below sea level, below the x-axis. Well, okay, so I heard something, 4 to 6. Okay, everybody see? So he's walking along this terrain here, and he's walking down this hill. Right at 4, he goes underwater, so to speak, goes under the x-axis, and he comes out again at 6, right? So this region, from there to there, he's below the x-axis. Now, what about the boundaries? 4 and 6 are the boundaries. Do we include those values? Is the ant, what are the ant's coordinates at that place right there? Okay, so his x-coordinate is? and his y-coordinate is 0. Now down here, this is different. Down here, his x-coordinate is 5 and his y-coordinate is some negative value, right? But that's, my question is that negative value then? Is 0 negative? It's not. It's between negative and positive, right? It's a boundary is all it is. So would I include that endpoint then? No, he's not below the x-axis there. That's right when he hits the x-axis. So we'd have to put an open endpoint there. Everybody agree? Because it's not negative valued there, nor is it negative valued there, right? If we were to squeeze that region right there onto the x-axis, wouldn't it just look like open endpoint and a line segment connecting it to another open endpoint? How do I write that? That's not a big deal. We can do that. How do I write that interval on the x-axis? X is what? Okay, so it's less than 6 and greater than 4. There you go. So that's one interval. Agreed? Okay, we need another one though. Okay, so now what about that? Take a look at that other interval. How are we going to deal with that one? So what do you think here? We got this interval. What about where else could the ant be walking and be under the x-axis? Okay, so -1 appears to be kind of the boundary. Is he going to want to be to the left or the right of -1 to be below the x-axis? Everybody agree to the left? So here's the boundary. And as he walks to the left of -1, he's down here below the x-axis, right? So this, we wouldn't include that -1 though, his y value is 0, right? So we wouldn't include that point, but everything else we would. Now if I were to squeeze that interval, that infinite interval where the ant is below the x-axis onto the x-axis, wouldn't it end up just looking like this? I'm going to get an open endpoint and then it's just going to extend to the left of that forever. Everybody agree? All these points down here, if I squeeze them up onto the y-axis, they're just going to be points on this region, right? Okay. How do I say that interval? X is what? Less than -1, right? So I get two intervals. I get this interval over here, this interval there. So how would I connect those then? If I want to say every place where the ant could be below the x-axis, would I connect them with the word and or or? Well, let's debate that. So x is less than 1 and x is greater than 4 and less than 6. What's wrong with that? You're right, Connor. What's wrong with that? Thank you. What's wrong with an and statement there? You're absolutely right. We can't use it. Ideas? They are mutually exclusive. That's exactly the right word. You can't be in both places at the same time, right? The ant can't be here and here. He has to be walking on this region or that region, right? So we connect him with an or, and that's our symbol for or right there, right? So really our answer in Moodle is just this or that, right? That's how we'd input that in Moodle. How would we input that using interval notation? Because we get some questions like that also. If we wanted to use interval notation, how would we say this one? X is less than 1. That means we've got an upper boundary at -1, right? So I'm going to have my upper boundary be -1. How do I say in interval notation there is no lower boundary? Negative infinity. And I'd have to use a rounded bracket. I have to use a rounded one there too, don't I? Because I'm not including the endpoint, right? In interval notation, we would just put a comma between all the separate intervals. So I get this interval or this interval, and that one's just going to be what? How do I say this with interval notation? 4,6, right? I have rounded brackets because I'm not including the endpoints. No big deal, okay? If this question were different and it asked where is it positive value, well then we're just asking for the places above the x-axis, right? You get the idea though, okay? So next one. So positive value to negative value is fairly simple. What about decreasing and increasing though? Because that's the next question. That's the other characteristic we're going to look at. We're going to look at where are functions positive value to negative value and where are functions increasing or decreasing. This is ironically the very same thing we're doing in calculus right now, but just, you know, at a different level is all, right? So where is a function decreasing? Let's define that. What does it mean for a function to be decreasing? Let's start with just describing it and we'll get more mathematical later. Say it again. That's exactly negative slope. Okay. In terms of an ant, how could you describe that? As an ant, describe what an ant would have to do as he walks along a function. Okay, he has to go downhill. Agreed? Mm-hmm. He has to go downhill. But down, we have to be a little bit more particular than that. If we say just walking downhill, like I could start an ant right here, and if he walks this direction, he's going downhill, but that's clearly not decreasing. Down to the right. So as the ant walks in the positive x direction, from left to right, is the ant going uphill or downhill? If the ant is going downhill, then the function is decreasing as he moves in the positive x direction. If it's going uphill, then it's increasing, right? Everybody agree? Yeah. Okay. So then where on this graph, let's define the places where the function is decreasing. Okay, it looks like, everybody agree, -6 appears to be the peak of that little mountain that he's walking along, right? And 2 appears to be the bottom of that valley, right? And so everywhere between here and here, for sure, those are places where he's decreasing. Now, the question becomes again here, though, do we include the endpoints? What do you think? Everybody, let's take a vote. How many people think we should include the endpoints, that the ant is decreasing right there, for example? How many people say we should not? Oh, you guys are good. We should not. You're right. We should not. Those have to be open because those are the transitions between increasing and decreasing. They're neither one of them, right? It's kind of like 0 is neither negative nor positive. So if we were to squeeze that interval down to the x-axis, then would everybody agree that it just looks like the interval from -6 to +2 and everywhere in between? We're not including the endpoints, right? Yeah. So how would we say that using an inequality? X is
definitely
less than 2 and
greater than -6.
Okay, that's it. So that's the interval in which the function is decreasing. Okay, increasing would be where? So if we do increasing in green, what would that look like? Say it again. 2 different spots. Where's one of them? Okay, so -10 up to, but not including, right? So we'd be on this interval where we have a solid endpoint because he can stand there. And if he steps to the right, he is going uphill, right? So he is increasing there. But when he gets to the peak, he's no longer increasing, right? So that interval would just look like what? X is, you tell me. Walker, what's that little interval going to be right there? X is doing what? So he's walking uphill from that point to that point. So it's increasing, but tell me, I want to know what the interval is there. How do you define that whole interval in terms of using an inequality? X is greater, you continue, greater than, good. Do I use greater than? Or equal to, good. Then -10 and
Less
perfect. Okay, good. And then what about the other interval over here? What's that going to look like? This other interval, he's going to start where? Increasing. At 2, good. But he's not increasing at 2, is he? Just like he wasn't decreasing. So we've got to put an open circle. He's going to increase all the way on up. Do I include the endpoint? I mean, I would if I could, but can he go to 6? So he can't increase there, right? He can't even step there. So we have to have an open, because we'll say the function's not defined there, right? So then this one would be, what's that interval going to look like? X is less than 6 and greater than 2. And we would just connect those with an OR. right? Get the idea? So we could be a little more particular, a little more mathematically precise with that increasing, decreasing thing, if we think of it this way, right? Here's how we could define mathematically. We use our informal definitions, what we would call what we just talked about it now. It's informal because it's not really very mathematically precise, but it works. It gives us a really good idea of what increasing and decreasing means. As we move in the positive x direction, if the ant is walking uphill, it's increasing. As we move in the positive x direction, if the ant's walking downhill, it's decreasing, right? Or we can think of it in terms of a slope. Here's our really ironclad, mathematically precise definition where there's no loopholes. If B is greater than A, right, so B is just some number that's greater than A, wouldn't you agree that when I put B into the function and A into the function, if the value of the function at B, meaning if the Y value at B is greater than the Y value at A, and B is greater than A, so B is to the right of A, that means increasing, doesn't it? Right? If for a larger x value, a greater x value, the value of the function is bigger, then the ant must have been walking uphill. So that's our mathematical way of saying, yeah, for sure that means increasing. If B is greater than A, but the value of the function at B is less than the value of the function at A, then the ant must be walking downhill. Okay? So the last issue, and we don't really need to do anything with this one, I just wanted to define these terms, is, we can skip that. Let's go there. Maxima and minima. So that's the plural of maximum is maxima, right? The plural of minimum is minima. But a maximum occurs where an ant is at the highest point, right? Does this look like a maximum to you right there? I mean, I see kind of both a little bit. Why are people shaking their heads no? Because I can see why maybe they wouldn't. What do you think, Jake? Why, can you think of a reason why we'd say maybe that's not a maximum? No?
Because there's lines with higher.
Okay, so there are other points up here that are higher than that one, right? So you're right in the sense that we would say it's not a global maximum, meaning it's not the highest point anywhere on that the ant could possibly go. That's true. But it is, and more importantly, and this is what we focus on in math more often, it is a local minimum. We also call these relative extrema, so a relative maximum, not minimum. It is a local maximum or a relative maximum. Why would we use the word local or relative, do you think? Because you see it on the graph, and the ant could, if he's hiking through this terrain, when the ant stands up there, he feels like he's accomplished something because he can look around in any direction, which for the ant, he's only got two directions, either forward or backward, right? If he looks in those directions, he's going to say, yeah, I'm at the highest place around, right? Oh, there's some peak in the distance that's higher, but that's for another day, right? For today, he can plant his flag up there and say, yeah, I did it, right? I climbed this peak. There's something special about being there because it's the highest place, locally speaking. Local to him. Around that point, it's the highest place. If he walks forward or backward, he's going to end up lower than he was before, agreed? So it's a maximum, right? What is a maximum? It's just a transition from increasing to decreasing, isn't it? Right? On the function. That's all it is. Okay? But it's only relative because there might be other places he could go that would be higher. When he walks down into this valley, he can get down to the bottom and say, wow, this is pretty cool. I'm down at the bottom of this deep canyon, right? If I walk forward or backward, I'm going to be higher than I was before. And so that definitely is kind of significant. It is a local minimum because relative to the places right around him, it's the lowest place. Could he get someplace lower? Yeah, if he hikes clear over here, he can go down forever if he wants to, right? But locally speaking, he's in the bottom of that valley, and so it's a relative minimum. Or a local minimum. That make sense? Everybody get the idea? Okay. For now, that's all we need to spend. I mean, we don't really need to. So this is a transition between decreasing and increasing, right? Local minimum just means he's going from decreasing to increasing. Okay? Go. We can work on this stuff.